Professor Huang. So I'm here to do the last talk to do the time control, so I will make sure we stick to the schedule. So my talk will be flexible and short. Portugal, I promise I'll give you enough time. Okay. So today I just share a little bit about, because I have seen so many talks about very fundamental talks, also modeling talks, materials. So I share a little bit more about the firefighting part. I think this is not really addressed in today's talk. So let me start with a question I have been thinking for many years. Is a battery fire a material problem or a fire problem? So because that's something really determining whether it should be the material scientist be the center of this battery safety, or actually eventually it's fire engineering's job. So I don't have a good answer for this question. I share some videos to you. So this one is in a gasoline processing factory, and you can see some worker is trying to clean up the containers, but unfortunately the gasoline is so flammable, even a friction generates the arc to cause the explosion, causing the fire. So the gasoline is really dangerous, and I also see many of these short videos, people playing with the gasoline in a very dangerous way. They don't even realize gasoline is really dangerous. But the question is why we do not worry so much about the fire safety or the fire hazard of gasoline, and everyone talk about the EV car fire. Not too many people talk about the gasoline car fire. So that's something I really don't know how to explain. Until one day I saw this video. It's in a gasoline station, and you see someone forgot to take out their pipes. And so it's a very dangerous fire. But what surprised me more is some random guy from the street just took some fire extinguisher and they control the fire within 10 seconds. So this is really impressed me, because I also teach my students the flash point concepts. The gasoline has very low flash point. It's one of the most dangerous fuel you can think of. But some random guy in the street can handle it in 10 seconds. So this is the reason we don't really worry about the gasoline fire, although it is considered as one of the most dangerous liquid fuel you can find on Earth. So is the battery fire a material problem or fire problem? So no matter what answer to this question, I have listed a rank of the material fire safety. So no matter how safe the battery is, I don't think it will be more safer than wood or plastic. No matter how unsafe the battery is, it cannot be worse than gasoline, so it will always be something in between, right? So no matter how the battery material involved, it will also follow in that rank, no matter what kind of technology involved. So that's my thinking. So whatever material science to do, you cannot change this rank. So, but what can be changed is the fire protection system. The fire protection can make a gasoline feels like not so different between from the wood or plastics. So if we can do something good, we can also make the battery no different than plastics and wood. So let me get to another question I'm also thinking about is, what is the probability of a battery fire? So I think insurance company also consider that a lot, and also manufacturers, also warehouse, many people will consider these questions. I don't know the answer, but let's change the question. This question every fire engineer knows. So what's the probability of building fire? So all fire engineer will give you that simple answer, 100%, because we assume the fire will happen. So what's the probability of having fire in this room or this table? 100%, because even we do everything so well, some crazy people can come here and do awesome things. So the fire will always happen. So it doesn't matter, because as a fire engineer, we make sure even the fire happens, we control it. Even the fire happens, we make sure people can evacuate from this room in a very safe way. So this is a reason for all the building design. So why do we have 2 staircases for the building, for the high-rise building? Why 1 staircase is not enough? Because we need to make sure even the fire happens, 1 staircase is compromised, we still have another staircase to use. That's the reason almost every building in Hong Kong or in many other cities, you have equipped with very expensive sprinkler system. The sprinkler head is very cheap, but think about the pipes, the space it takes, the maintenance cost of the sprinkler system. So expensive. Even it's expensive, we still install it because we know fire will happen 100%, even by accident. So we need to make sure the fire happens. Even the fire happens, we control it, we can handle it. So this is the principle of building fires. So if you ask any fire engineer, they give you 100% answer for the probability of building fire. So I'm a fire engineer, so I give you the same answer. What's the probability of battery fire? 100%. Because no matter what kind of test you do, I'm sure some random guy can use some way you cannot think of to trigger that battery fire. So this is the principle. So how do we fight the battery fire? So you see a lot of these videos, like firefighters go to the fire scene, see some electric vehicle burning, and I don't know what to say. It's kind of like useless, right? So sometimes I also talk to the firefighters, you should just cover the vehicle instead of embarrassing yourself, because people will take these videos and put online. It seems like you're not doing anything. So if we cannot even stop the fire in a very small electric vehicle, so how can we handle, like, you have a massive electric bus burning in the square, and so that's impossible. And it also reminds me something we handle a lot in the building fire is when the building fire is completely out of control, you can see firefighters are not really extinguishing fire. They just watch it and wait for the all field burn out. Because essentially, there's no way you can stop a building fire like that. It's very similar principle as you cannot stop massive car parks full of electric vehicle burning outside. So let's take a close look at what's the process of battery fire and the compartment fire. So yeah, let me start this video. So this is like a regular fire. You see the battery venting is on. Could you turn off the sound? Yeah. So this is a video accelerator. Okay. So you can see you have the venting, you also have the fire afterward, right? So let's take another look at of a very common room fire. So this is the fire in a very standard living room, and the Christmas tree was ignited, very common in the Christmas holidays. And you can see the fire will develop and spreading in the confined space, and eventually it will reach some state called a flashover. So how long it take? In this case, you can see just after 30 seconds, it's almost getting to the rabbit in front. And it takes about 40 seconds to ignite the rabbit. So essentially, the flashover happens. So if we take a closer look at the battery pack and a very typical floor plan, you will see they are so similar. If we consider each cell is each room. So maybe we can consider one small cell is the same as one small room. And when the flashover happens, you will see something very clear is you have that flame coming out from the room. They are seeking additional oxygen outside. So we call that spilled flame. So that's very similar you have the flame coming out from the battery, right? So if you consider these small elements, they actually look so similar. And if we look at the development of the temperature of these, any kind of these small cells, you will see there are clearly two in vent. One is a venting, the other one is a thermal runaway, we call. And if we put the building fire or compartment fire, room fire, as a comparison, we always have a 4 stage of the compartment fire, from the ignition to the fire spread. Then we have the flashover event to fully developed fire. So it actually is so similar if you look at the thermal runaway and flashover. So I remember 8 years ago, I met Professor Xinyan Huang in a conference. I asked him, so I asked the question, why do we call battery thermal runaway? Why don't we just say ignition? Well, I remember Professor Wang said, okay, because it's the terminology, battery community is defined, it's not fire engineering defined this terminology. But after many years, I realized, no, actually it's not ignition. In fire engineering terms, the thermal runaway is flashover, because that's the moment you have the flame coming out from a confined space. And whatever after that, it's useless in firefighting. So that's what we see. So you have the building and you have massive fire engines not able to stop the fire. That's the same reason, the same thing, you have multiple fire halls cannot even handle electric vehicle fire. So thermal runaway is not ignition, it's actually flashover. So what is ignition? I think venting is ignition. After you ignition, think about if we ignite this table in this room, so the smoke will coming out. So it's very similar to venting process. You have some smoke coming out from the confined space. So that's what I'm thinking, okay, maybe this is really the ignition of the battery, not the thermal runaway. Actually, venting should be considered the ignition of the battery fire. So how do you traditional firefighters or fire protection system to protect our buildings? We have multiple ways. During the ignition stage, we will have smoke detectors in the room. So when the smoke come out, you will send out some beep, although you have a lot of false alarm, because when people smoke in the room, you also trigger the smoke alarm. Okay, but it's fine. We also have other things like sprinkler system. So if you have some small flame, maybe this table is igniting, it will come out with a very long flame and quickly trigger the sprinkler, and the sprinkler will suppress the fire. Even the sprinkler is too weak to control the fire, you can delay the thermal runaway. So that's a principle. Then, with the collaboration with the firefighters can come, so the sprinkler give additional time for the firefighters to stop the fire, also give people time to evacuate. So this is a design principle for the building fire protection. So what's our current design for the battery? So we have a lot of things. For example, we talk about the gas sensors. We talk about measuring hydrogen, other kind of signature gas for the battery thermal runaway. Yes, we have these sensors for the battery, and of course, a lot of false alarm, just similar as smoke detector inside the room. So one thing is missing is we don't have the sprinkler for the battery system. Where is the sprinkler? Before the thermal runaway or before the flashover. That's something actually missing here. So everything dealing with battery fire is after the thermal runaway, but that's already too late, because we all know when the thermal runaway, when the flashover happens, we cannot do anything for the building fire. Same thing that we cannot handle thermal runaway of the battery fire, because it's already too late. So that's the reason we did some little experiment in the lab. We use a laser to ignite the battery, and now the venting happens. And we keep using laser to ignite it, to heating it. And as you can see, even we continue to heat this battery, it still takes about 3 to 5 minutes before it actually went through the thermal runway. The video is accelerated. So you can see after about 5 minutes, you have a very strong thermal runway and a flaming. So if you take a look at this time evolution, you can see a clear time window here. That is between venting and a thermal runway. That time window can vary from 1 minute to 5 minutes, depending what kind of battery you are testing. So you have a time window here. You can do something. But I don't think any company in the world is doing anything for this time window. You just let it happen. You just let the thermal runway happen. So can we do something? Can we have some sprinkler system for the batteries, a sprinkler, not a real sprinkler? So that's what we did in the lab. So my student, they did all these experiments, and he is designing a very smart device. He used magnetic induction heating to heat the battery. And once it starts to venting, he will drop some cooling agent and see how much of the agent is needed to actually stop the thermal runway. So of course, if you put a 2-liter amount of the cooling agent, the thermal runway will continue to happen. And if you put it too much, then you are wasting a lot of the cooling agent. So what we want to do is trying to find out the minimum amount of the cooling agent that actually stop the thermal runway happen after the venting. So you can see on the left-hand side, clearly we don't put enough cooling agent. So the smoke is keep running, and eventually it evaporates all the cooling agent. So the thermal runway will continue happen. But on the right-hand side, we have enough cooling agent. So you can see bubbling coming out, but the battery eventually is not going to the thermal runway stage. So now let's look at the temperature profile. So this is just using some water. If we put too much water around the vented battery, the water does not even reaching the boiling point. So we are putting too much water. So let's reducing the amount of water, and you can see eventually the battery temperature will fixed in the boiling temperature. So it cannot go higher before you burn out all the water. And we found a very interesting result. You only need 1/16 volume of the battery water to stop the fire. So for for the 18650 battery, it means you only need 1 milliliter water. After the venting, you can stop the thermal runaway of the fire. So, of course, for different SOC, you have different requirements. A higher SOC, you need more water or other cooling agent to cool it. And we tested 4 different types of cooling agent from the different transformer oil, silicon oil, and dielectric liquid, as well as the water. And the similar thing is you can see approaching the limit, all these liquid will enter the boiling stage, because eventually the limit is controlled by whenever all these cooling agent is evaporated. So that gives you the limiting condition. So what I want to say is we should do cooling early, not later. So you have to do the cooling before the thermal runaway happens. Of course, I'm not telling you to randomly spray water to a normal operating battery. That's definitely harms the whole system. So what I'm saying is you should do cooling when you are very confident to know if the battery will go to the thermal runaway. But clearly, we are not doing anything on these things. What we are doing is putting a thermal runaway battery into the water, and you can see even you put a car into the water, you still have the flame on the surface. So that's not anything water or other firefighting techniques can solve this problem after the thermal runaway, because it's already flashed over. You have to do something when you see the ignition just happen. I think venting is a good moment to define that ignition, the battery ignition moment. Of course, we just did a very small battery cells. We don't know what's going on for the large battery or what's the scaling law for these larger battery, whether satisfying this limit or the venting design, whether is something can be adjusted. So a lot of research can be done for bigger batteries. And I talked to my ideas to some of the battery manufacturers. They give me some feedback. They say 5 minutes is not enough. So I know, even I know the thermal runaway happens 5 minutes after venting, it's not enough for me to design a good system to protect our battery. Then I show this video. Okay, so this is a very typical sprinkler system installed in the building. You can see a normal sprinkler system can activate within 1 minute or 2 minutes. So it's actually very simple design. The sprinkler has 150 years old history. It's very old technology. It can handle within 1 minute. You tell me you cannot do it within 5 minutes. And I show another one. So this is an airplane caught fire. And you can check the timing. It's not accelerated. So within 1 minute, you can see more than 100 people evacuated from this airplane. If 100 people can evacuate from airplane within 1 minute, don't tell me you cannot do anything for the battery in 1 minute. That's not a good excuse. Okay. So anyways, because I'm a fire engineer, so I learn most of my things from the building fire. So I think it's good to always look back, think about what fire engineers have been dealing with building fire, because it has been working in this area for more than 150 years at least. So we have established a lot of things in the building, and we can always learn these techniques from the building fire protection. So according to the European standard, we have 7 layers of fire protection for building. So here I'm proposing the 7 layers of fire protection for the battery fire. And what's missing here is the early suppression. So the thing is, we know the battery will go to thermal runaway, and we do nothing. That's something, as a fire engineer, I cannot accept. We don't think we are doing good enough. And of course, I hope everyone here can work on this area together to make the system much safer in future. And finally, I'd like to thank my group, and also they are the volunteer of this conference. And I cannot do all my research without their support. Thank you all.
Thank you. Thank you very much. It's a new opinion on the battery fire compared with the building fire. So we can have 2 or 3 questions or comments. Oh.
Thanks, Professor Xinyan, and it's a very interesting and impressive presentation. Your first question is if the thermal runaway is a fire problem or the material problem. Maybe, I just want to tell you maybe the cold, ugly truth is each of the time of the charging and discharge of the battery is a hurt to the battery material and its structure. So it's unbearable. But the battery manufacturer will never ever tell you. The truth is, every charge and discharge is doing harmful to the battery structure and its material. That's it. Thank you.
Thank you. Yes, I think the material degrading is also something sometimes we did not really look into it. Because for example, for the wood, for the plastic, even you take 20 years, 30 years, I don't think the flammability changed that much. But yes, the battery definitely will change a lot within just 1 or 2 years. Yeah. Thank you.
And more questions? Oh.
Thank you, Professor Huang. I'd like to share my understanding on the thermal runaway of lithium-ion battery. Let's thinking about the dynamite, such as TNT. In the view of chemist, I think the most drastic reaction is redox reaction. And for TNT, the oxidant and the reductant, they lies in one molecule. I mean, the distance between the functional group is within nanometer. And for the lithium-ion battery, the distance can grow into micrometer. So in this sense, I think the thermal runaway is not lies in how much chemical energy in the molecule. It lies in how fast the energy can be released. So in this sense, I think gasoline is safe because the oxidant is meter away from the energetic material. You're talking about the time window. Just as I talking about the chemical crossover, I think that is a flash time. So if we let the chemical crossover happening, that means we send the reactant to the oxidant. So the distance between the two species will be a nanometer. That will be dangerous. And so the best time for us to stop the chemical crossover as much as possible and as early as possible. Thank you.
Thank you. Very, very good comments. And yeah, next time when I rank these things, I will put a TNT before the gasoline. And before TNT, I will put another thing that is more dangerous, is human. Because most of the fire are started by human mistakes. So, thank you.
Thank you very much. The last question. Oh,
Thank you. Thanks a lot for the very interesting analogy, Xinyan. I found it very interesting, very unique. So my question's regarding your comments on suppression and so on. I mean, I've been talking to quite a few OEMs and so on for battery systems and modules, and there seems to be a bit of a push towards active cooling systems. So rather than suppressing agents and so on, or trying to embed it within modules, things like active liquid heat exchanger type of systems and so on. I mean, given that it seems like the enthalpy requirements to kind of arrest the heat up or the self-heating process, from what you've shown, doesn't seem to be so significant. What are your thoughts on that? Do you have any comments?
Thank you. So this is a very good question. I actually was talking to some friends from Huawei about the battery cooling, whether they can using the cooling plate to solve the battery fire problem. So the simple answer is no.
Oh.
It's basically what you are asking is using the air conditioning system to cool the fire, or using the air conditioning duct to ventilate the fire smoke, because they are completely on different capacity. Of course, I'm not saying if you install 100 air conditioning in this room, you cannot cool the fire.
Right.
Of course you can, but nobody will do that, and no one will use normal condition for the emergency. The normal operation should not be able to handle the emergency because it's too expensive. If you design under that principle, it will never work.
Okay. So good job security for us 5 people then.
Thank you.
Thank you very much.